Okay, this is our final video on our space physics topic, and we're just going to look at quite a wide range of topics, both in subject content but also in distance and size. We're going to think about solar system, and then the main bit that is mentioned on the specification is dark matter and dark energy. So we're going to think about planets, understand the size and scale of the universe, and know how scientists are trying to work out exactly if dark matter and dark energy really exist, because you'll probably realise after watching this few minutes of video that there's more questions than answers. Okay, so some sun facts, true or false. You can kind of pause this if you want and have a guess. The sun accounts for 99.86% of the mass in the solar system. Well, that's true. Over 1 million Earths could fit inside the sun. Yep, it's that big. That's true as well. One day the sun will consume the Earth. Well, yep, it's going to turn into a red giant. So that's true as well. The sun travels at 220 kilometers per second. Yep, that's how fast it's going. You get the pattern with these, don't you? The sun will eventually be about the size of the Earth. Yeah, towards the end of its life, if you've watched the videos, when it eventually will turn into a white dwarf. Well, yes, that's true as well. It takes 8 minutes for the light to reach Earth from the sun. Yep, true. The sun is about halfway through its life. Yeah, it's sort of 4 to 5 billion years through its lifetime, with an expected life of maybe 10, 11 or something like that. The sun has a very powerful magnetic field. Yes, it does. You can see evidence of this with all the solar flares, etc. Temperatures inside the sun can reach 15 million degrees Celsius, and you may remember that from your study of nuclear fusion. So yeah, all true, quite astonishing facts. The planets, you don't need to know these facts for the exam, but again, just to put this lesson into context, it is good to have an understanding of the physical size of our solar system. So going out from the sun, we've got Mercury, Venus, then Earth, where we are. So the length of the year, you can see much shorter year, and then we get to Earth. Our year is the standard, the 1 year. So Mercury is sort of a fifth of our year is the year. Venus just over half. Mars a couple of years. You can see the temperatures, so sort of starting off good range for Mercury, but then slowly getting cooler as we move out. If we go to Jupiter, so our year is now nearly 12 Earth years, and Saturn, Uranus, Neptune. Getting much cooler as we go out. We're down to sort of minus 201 degrees Celsius for Neptune. Exoplanets is mentioned on the specification. So what's an exoplanet? Well, planets that are outside our solar system, so they're orbiting other stars. As of Feb 2016, there have been more than 2,000 discovered, but the estimations are that in 5 sun-like stars have Earth-sized planets. So there could be 11 billion habitable Earth-sized planets in the Milky Way alone. So this is like an astonishing amount of planets that could well be habitable, just like Earth is. How do we find them? Well, the clever thing is, obviously, the artist impression picture you've got here is just that. You wouldn't be able to see that detail because they're that far away, but we notice them from drops in light from distant stars. So if we look at the light from a star, it dims as a planet passes in front of it, and you can, if you watch them for long enough, you will be able to work out how many planets and what size they are going around them. You can actually get quite a lot of information from that. Okay, so moons, there's lots of moons in our solar system. There's obviously our own moon. One of Saturn's moons has got a solid water ice crust. So these are the matter of much discussion as to whether they can or do support life. Europa is the famous moon of Jupiter. It's the 6th largest moon in the solar system, a little bit smaller than our moon, and there's more liquid water in Europa than there is on Earth. So with the hot vents at the bottom of the oceans, just like the theories that that's where life got going on Earth, we've got sort of the discussion as to whether there could be life on Europa. Okay, so how do we talk about distances? Meters and meters per second are quite awkward. They're just not really a big enough scale to talk about the solar system, even the solar system, let alone the Milky Way and the universe. So we've got this thing called the light year. Now, light travels at 300 million meters per second. The thing to remember how fast that is, it will go 8 times round the Earth in 1 second. It's 150 billion meters from the sun to the Earth. So light would take 500 seconds to reach us. Okay, so if you think 500 seconds is about 8 minutes. So that's how long it literally takes the light to get from the sun to the Earth. Now, this idea gives us the concept of a light year. So a light year is the distance that light would travel in 1 year. And remember, to put that into perspective, it takes about 8 minutes for light to travel the distance the sun to the earth is. Okay, so a light year is the distance that light will travel in 1 year. So let's try and put this into perspective. The sun to the earth is 500 light seconds. So light to go from the sun to the earth is 500 light seconds. And then the next one up will be the solar system. So light to cross the solar system all the way through all the planets we've just discussed would take about 5 light hours. Okay, so the distance, sorry, not time, the distance would be 5 light hours, which I know it's strange saying distance, but again, this is the distance that light would travel in 5 hours. Then we've got, next up, we've got the sun to our nearest star will be 4.5 light years. So the distance to our nearest star, light takes 4.5 years to get there, travelling at the speed of light. And then we can consider our galaxy, the Milky Way. So there's more than 100 billion stars in our galaxy, and its total diameter would be 100,000 light years. So that means that light, the distance that light travels in 100,000 years, that's the diameter of our Milky Way, approximately. And then we've got the universe, before that we've got the local cluster of galaxies. So the universe is split into what we would call little clusters of galaxies. Our local cluster is 2 million light years. So to get across our local cluster, light will take 2 million years to do it, and that's going at the speed of light. And then finally the mind-bending one, the universe, where there is approximately 100 billion galaxies, takes light 13.7 billion years to get across it, and this is how we come to the age of the universe. Okay, so keywords, just make sure for GCSE you've got to know light year, planet, star, galaxy, Milky Way and universe. If you can't put things into perspective, then you are going to struggle to understand any questions and to answer questions convincingly. Okay, so just make sure you know your definitions, and we've talked a lot in the last few minutes about what these things are. Okay, on to the two most important bits in terms of what the specification mentions. Dark matter. Some of the observations of the universe are sort of strange, and they cannot be explained using current theories. If you look at the animation we've got here, this is the idea of a galaxy. So we've got the sun, or a group of stars, which sort of looks like a sun, but this would be a group of stars in the centre of a galaxy. So the brightest bit of a galaxy, where there are many, many hundreds of thousands, millions of stars. And what should happen is, because as stars get close to this, they should spin faster. And because if most of the mass is in the centre of the galaxy, or the Milky Way, then they should be, the gravitational attraction in the middle will be much higher. So therefore things closer would have to spin much faster. And you can see as you go out, the rate of spinning decreases significantly. Now this picture on the left is what galaxies should spin like, but this picture on the right is actually what galaxies do spin like, and you can see there's not that much difference. It's not like going around exactly the same speed, but they're moving significantly faster in the outside than they would do in the expected model. And the reason it's expected is this: if you look at this first graph at the top, this is the orbital speed of the planets as they go out from the sun, and most when you look at this, they should follow this sort of quite predictable curve here. So you can see that Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and you've got like them all on this plot. And this plot shows that as you increase the distance, you decrease the orbital speed. Now, if we have a look at this bottom graph isn't the solar system. This is stars in our galaxy. So now you can see the distance from the centre of the galaxy, centre of our Milky Way, as that increases, rather than the orbital speed sort of decreasing, it's sort of like there's a few fluctuations in it, but then it sort of levels off. So this sort of really is strange. This is not like the planets going round a sun model. So the normal gravitational field ideas, with most of the mass being in the centre, just don't work out. Okay, so this is sort of like really the crux of it, this galaxy rotation problem, and you can see that the idea that dark matter comes from, that this is what we see, the speed from the centre of a galaxy is what we see, this is what we expect, and the reason we expect that is we expect most of the mass to be in the middle of the galaxy. But we need another theory, and the theory that science has suggested is that only the matter that we can see that isn't just the only matter that there is. So there must be a lot of missing matter in our galaxy, and this missing matter is what is being called dark matter. And the existence of dark matter has allowed science to explain these observations of the galaxy spinning in a strange way. And so the suggestion is that there must be an awful lot of matter outside of the galaxy, right away from the centre, and even beyond the planets, beyond the stars at the edge of the galaxy. Okay, so this is the proof, if you like. I mean, you've got to be careful saying the proof because it is only a theory, but that there is lots and lots of missing matter, and there must be an awful lot of it outside of the centre of the galaxy, right out beyond what we would see as being the stars associated with the galaxy. Okay, and the second thing, just to mention very quickly, dark energy. These diagrams are important to sort of get your head around. There's maybe three theories for the future of our universe. The Big Crunch. So initially we've got the Big Bang, and the Big Bang, the universe has been expanding, and in present time it's currently expanding, but will the expansion slow down, and eventually maybe the universe will contract again? There's the Continue Forever theory, where we've got the Big Bang, and then we've got an expansion, and eventually it sort of levels off with the expansion rate really slows down. And then we've got something called the Big Chill, where the rate of expansion keeps on going, and if anything it's increasing. The expansion is getting more and more and more, so eventually everything's that far away from other, and the energy in the universe is that spread out that people have suggested this could be called the Big Chill. So evidence for these diagrams, well, theory suggested that the expansion of the universe since the Big Bang should have slowed down. So really we should be on sort of one of the first two graphs, the Big Crunch or the Continue Forever. But the opposite is actually happening. The rate of expansion is increasing, and we haven't really got an idea as to why this is. If things are getting further and further apart, the gravitational theory suggests that the rate of expansion should decrease, but this isn't what's happening. From redshift measurements, which we talked about in one of the videos earlier, redshift measurements show that the further stars, the further away the stars are, they are actually going faster. So we've got this idea that things, the rate of increase is increasing. Whatever star you look at, they're all getting more and more fast as they move away from us. So this is a strange idea that somehow empty space has almost been able to create a form of repulsive gravity. There's almost like a pressure on the universe to make it expand outwards, even though it can't be our sort of normal mass or normal gravity that's confusing it. And this pie chart is that sums it all up really, that dark matter, current calculations, that dark matter, which is driving the galaxy rotation problem, is about 20% of the universe, 21%. Normal matter is about 4%. That's the stuff that we're made of and planets are made of. And then dark energy must account for another like 3/4 of it, 74% of the universe. And this is what's causing the universe, the rate of expansion of the universe, to increase. Okay, and I've just put here, like, are you confused? Well, yes, you probably are, but that's absolutely fine. There's a couple of videos here to watch. I'm sort of suggesting from YouTube. Okay, the two videos. This is the first one. It looks a little bit like this. What is dark matter? And then Neil deGrasse Tyson. This is sort of worth a watch. It's a lecture in 2011. Again, sort of saying that we don't really know. So I would sort of suggest, if you have got time, just to kind of have a look at those two video clips. But the main thing you need to do for the specification is a basic understanding of dark matter and dark energy.